Uh, so far we in nonlinear systems we have studied different types of nonlinear systems, and we have actually studied uh, what are the commonly occurring nonlinear behaviors in in nature. So we'll start with the analysis, and that actually includes the mathematical modeling of mathematical realization of these systems. Right? Instead of writing the mathematical realization, I'll be writing the term modeling, because all of these behaviors are not actually mathematical, do not include mathematical derivations. Uh, so as we have seen in case of linear systems, we had the mathematical modeling using transfer function approach, using the state space modeling approach, and analysis we could have done using the frequency response approach, like that of polar plots or Nyquist plots, etc. So similarly, we'll be having certain mathematical tools, we'll be having graphical tools that we can extend to nonlinear systems, and using those tools we can actually uh, uh, determine the or analyze the behavior of a nonlinear system. So previously also, as I have told you, that we use a certain approach. So there are actually three main approaches that we use for analysis or modeling the nonlinear systems. One is the linearization approach. Second one is the describing function approach. And third one is the phase plane analysis. Uh, so these three methods can be used to actually obtain a model of the system or of a nonlinear system, and uh, using that model we can actually then be able to analyze the behavior of this nonlinear system, analyze for its properties. We can say which behavior it is exhibiting, limit cycles, bifurcation, chaos, where what are the equivalent points of the system, where the system is stable, etc. We can all determine that only after modeling the system, a proper choosing the proper approach to model the system and analyze the system. So the first one is the linearization approach. Linearization is the simplest of these approaches. We simply tend to mm, approximate a non-linear model of the uh, approximate a non-linear model of the approximate a linear model, sorry, of a non-linear system. आपके पास कोई भी एक नॉन लीनियर सिस्टम है तो उसको हम instead of deriving its non-linear equations, we'll instead of using the non-linear equation for analysis, what we'll be doing is इसकी जो basic equation होगी उसको हम linearize करेंगे, and from that linear equation we'll be able to analyze the system for its properties, for its stability, etc. So linearization will simply involve the linearizing the non-linear equation of that system. And we have the describing function approach. Describing function approach is actually an extension of Nyquist criterion. You can say to the non-linear model. हमने Nyquist plots वगैरह Nyquist criterion देखा है for a linear system. We can extend that to the uh, non-linear model as well, and describing function approach can be obtained. So it's actually nothing but a frequency response based approach, and what we do in this case is that the fundamental harmonic of the output of the system is actually compared with the sinusoidal input of the system. ठीक है. So for basically कोई भी एक system होगा, instead of giving now a step input, we'll be giving a sinusoidal input and we'll be analyzing the output behavior and its fundamental component. उसका जो fundamental component होगा, or the input component, that will actually give us the uh, it will be just like a transfer function, the ratio of the output, the fundamental component to the input of the system, while making sure we be able to get the amplitude and the phase of the system from that describing function. ठीक है. In other terms, जैसे हम ट्रांसफर फंक्शन में वाई एस बाई एल एस आर एस निकालते थे, यहाँ पे हम वाई वन और वाई नॉट वट एवर यू वांट टू राइट द फंडामेंटल कंपोनेंट निकालेंगे ऑफ ओमेगा एंड डिवाइडेड बाय द इनपुट कंपोनेंट. ठीक है. अब यहाँ पे एक इम्पॉर्टेंट चीज़ ये है कि जो आपका इनपुट होगा दैट विल बी अ साइनोसाइडल इनपुट एंड यू विल बी सीइंग व्हाट विल बी द फंडामेंटल आउटपुट ऑफ दिस पर्टिकुलर सिस्टम. ये जो रेशियो होगा, इस रेशियो से फिर हम एक्चुअली मैग्नीट्यूड एंड फेज निकालेंगे, जैसे हम पोलर प्लॉट नाइक्स प्लॉट में करते थे. We'll be obtaining the magnitude and the phase, and from that magnitude and phase we'll be able to get a plot, and from that plot actually we'll be able to analyze the system. So this is what we do in case of a describing function method. So the important thing here is actually obtaining this y by r or whatever the notations will be, as we'll see ahead. ठीक है. तो ये जो हमने लास्ट टाइम बैकलैश, सैचुरेशन वगैरह वो सब कुछ किए थे, डिफरेंट टाइप्स ऑफ नॉन लीनियरिटीज. So we'll be actually deriving the describing function of all those systems one by one and obtaining the output response. The third type of modeling approach that we'll be using is simply the phase plane approach. And phase plane approach is actually based upon phase variables or state variables, जैसे हमने already पढ़ा हुआ है. So it's again a graphical technique. And what we do in this case is actually we obtain the plot of states versus another state of the system. Okay? Say for example you have two state variables of any system or phase variables, so that will be calling out them x1 and x2. These are any state phase variables of a system. We'll be actually obtaining the plot of x1 versus x2, and from that plot of x1 versus x2 we'll be actually seeing whether our system is stable, whether our system is unstable, इसमें limit cycle behavior exhibit हो रहा है कि नहीं हो रहा है, what type of phase portrait it will be actually displaying. There are a number of phase portraits that we'll be studying, and what type of phase trajectories they will be exhibiting, वो सब कुछ हमें पढ़ना है. And from that we can actually find out certain points in the system. They are known as saddles, nodes, etc. वो saddle nodes actually हमें equilibrium points का एक information देता है, and about the stability of the system we'll be actually understanding that. So we have three approaches of analyzing a non-linear system: the linearization approach, the describing function approach, and third one is the phase plane approach. In case of linearization approach, we simply use a linear model of the non-linear system. We actually linearize the non-linear model. In the case of describing function approach, like the transfer functions, we obtain a ratio of this a mathematical model. That's actually nothing but the ratio of the fundamental output of the system to the input of the system, while your input is actually a sinusoidal input, and obtain the magnitude and phase from that mathematical equation, and from those we can actually analyze the behavior of the system. वो जो फिर यहाँ से हमें एक्चुअली एक इक्वेशन मिलेगी, that will be actually magnitude and angle plot. This will be actually known as the describing function of the system. ठीक है, ये describing function नहीं होगी. This will not be the describing function. This magnitude and angle का जो when we put it in a mathematical form, this will be the describing function of that particular system. It's simply an extension of the Nyquist criterion to the nonlinear model. And third method is actually the phase plane analysis. Just like we have the state variables, we can obtain the state variables for a nonlinear system. The difference here will be that our equation will no longer be a linear equation, it will be a nonlinear equation. X dot equal to ax plus bu is actually a representation of uh, a linear system. For a nonlinear system, instead of writing this, we'll be writing it's a function of x and u. X dot equal to f of x and u. Okay? So this actually hides the information about what a is here or what b is here. That actually will determine whether the system is linear or non-linear. So from that we can then obtain the state variables, obtain the plot of one phase variable versus another phase variable. Those trajectories, those portraits will actually determine whether our system will be able to determine whether our system is stable or not. What will be the limit cycles, chaos, etc. Bifurcation, saddle, more points. बहुत सारी चीज़ें we will all be understanding that from the phase portraits of these systems now. So now starting with the first one and the easiest one. We do not actually have to spend much time on this. First approach is the linearization approach. So what we do in case of a linearization approach, as I said to you, हमारे पास एक non-linear system होगा, उसका non-linear model होगा. We will derive a linear model out of that non-linear model. So we can do this in three different ways. One will be the linearization using small signal analysis. Second one will be the piecewise linearization method. And third one will be a frequency response based method, that is harmonic linearization. So now to obtain a linear model from a nonlinear system, again we can make use of three different approaches, and using these approaches we can actually determine the linear model of of that system. Now what are the systems that actually we can extend this approach to, not to a system that has hard non-linearity. जैसे मैंने आपको लास्ट में बताया, we have two types of non-linearities, hard non-linearity and soft non-linearity. Whatever systems exhibit actually hard non-linearities, linearization approximation cannot be extended to hard non-linear systems. It can be only extended to soft non-linear systems. Fine. That means basically soft non-linear systems में क्या होगा कि एक जो आपका सिस्टम होगा, सिस्टम का जो रेस्पॉन्स होगा, that will be curvilinear, you can say, sort of. We have a number of systems that actually exhibit this type of behavior. ठीक है, हर कोई सिस्टम एक लीनियर बिहेवियर नहीं दिखाता है. मोस्ट ऑफ द सिस्टम्स एक्चुअली एग्जिबिट curvilinear behavior. There are some there is a transient period during which their system will be actually exhibiting curved behavior, या फिर उसमें फिर हल्की सी saturation आ ही जाती है सिस्टम में at the end. The output will no longer be varying with respect to the input at the same. ठीक है, आपका system, say for example, it might begin saturating after some time, even if it might not be a total saturation, but output will not change with respect to input as much as it should be if it were to be a linear system. So there is a curvilinear approach in most of the systems. It is an inherent behavior in most of the systems. So this behavior can be sorted out using the linearization approximation. अब ये जो स्मॉल सिग्नल एनालिसिस मेथड है, इसमें क्या करते हैं हम, the small signal analysis, what we do is we actually make use of Taylor series to actually linearize the model, linearize the non-linear model of the system. And we do not need to make use of the entire Taylor series. We can actually use the first two terms. That will be sufficient for us for approximating the linear behavior of a system. If you remember, linear, the Taylor series somewhat like this. Uh, uh, x equal to x naught, the initial condition, x minus x naught squared divided by 2 factorial, and so on. So this is the Taylor series, but as I said to you, the first two terms of this Taylor series is actually sufficient for us to approximate the linear behavior. For linear approximation, we only take the first two terms. That means हमारा जो output होगा, that will be actually now f of x naught plus df by dx, while x tends to x naught, x minus x naught. Fine. So this, so हमारे पास जो भी equation होगी will actually be will be finding out its Taylor series using the first two terms of the Taylor series only, and a linear approximation can be obtained from that. Okay? So this will be possible only around the initial condition of the system. Now this x naught actually does not refer to the initial condition here. This actually refers to the equilibrium point. Since we have not gone into the details of equilibrium point, so not uh, I'll be using the term initial conditions for now. So what we have is the Taylor series. So this behavior will give us an approximate linear model of a non-linear system. अब हमारे पास सिस्टम क्या है, जैसे मैंने आपको बताया, x dot is equal to f of x and u. Fine. This is the state space model of the system. Now instead of writing x dot equal to ax plus bu that we normally do with a linear system, we'll be writing now from here on, we'll be referring to it as x dot equal to f of x u. Okay? For non-linear systems, we do not write ax plus bu. For linear systems, we do that. For non-linear systems, we'll be writing now f of x and u. This actually hides the information of a and b that actually is responsible for making the system non-linear in the first place. So what we do here is, so what will be the steps involved here to linearize the model now? अभी आपके पास एक इक्वेशन है किसी भी सिस्टम की, obtain its non-linear model. That's actually x dot equal to f of x u. Fine. Once you have the non-linear model, you need to then find out the operating points, okay, x naught and u naught. So for that you need to actually substitute this equation equal to 0. So that will actually give you the initial conditions of the system. So that means you need to find out x naught and u naught of the system by putting this equation, ये जो equation है, by substituting it equal to 0, you will be able to find out x naught and u naught of the system. Okay? So obtain x naught from here and obtain u naught from the system. So once you have done obtaining the operating points around which you actually want to linearize this system, then you can actually apply the Taylor's expansion to this. To obtain the initial conditions, you can say basically you can approximate the system to this thing थ्रू द टेलर सीरीज एक्सपेंशन। इसका मतलब है आपके पास अब एक सिस्टम है, उसका आपको डिफरेंशियल निकालना है, और वो डिफरेंशियल आप कैसे निकालोगे? बाय डिफरेंशिएटिंग दिस वेरी सिस्टम। And I can write it as a function of f naught x naught plus delta of xt what we are doing is we have actually a system f of xu, x dot equal to f of xu. You want to linearize it, and उसका output behavior जो होगा then that will be actually something like this: a delta xt will b delta ut. ये आपका नॉन लीनियर मॉडल है। The linear model of the system will be actually a function around the equilibrium points or the operating points, and the linear model of the system a of xt plus b of ut. अब इसमें खाली एक टर्म ऐड हो गई है, that's actually delta, where this a and b will be nothing but a will be nothing but the differential, the partial derivation of your function at around its operating points, and b will be the partial differential with respect to u around its operating points. So in other words, you can say del, and since this A matrix is actually A is a matrix, so delta f by delta x will be nothing but delta f1 divided by delta x1, क्योंकि अब इसमें n स्टेट वेरिएबल्स होंगे, तो n स्टेट आपके पास n डिफरेंशियल इक्वेशंस हैं। हर कोई डिफरेंशियल इक्वेशन का पार्शियल डेरिवेशन with respect to each and every state variable. First differential equation, its partial derivation with respect to n state variables, delta f2 divided by delta x1, delta f2 divided by delta x2, so on up to delta f2 divided by delta of xn, delta of nth derivative, nth differential equation, उसका derivation with respect to x1, del fn divided by delta x2, so on up to delta of fn divided by delta of xn, and similarly delta f by delta u will be equal to delta f1 पहली डिफरेंशियल इक्वेशन, उसका डेरिवेशन विद रिस्पेक्ट टू u, दूसरी डिफरेंशियल इक्वेशन, उसका डेरिवेशन विद रिस्पेक्ट टू u, सो ऑन, लास्ट डिफरेंशियल इक्वेशन, उसका डेरिवेशन विद रिस्पेक्ट टू u। ठीक है, सो in short we need actually once we do this, we'll be able to calculate A of delta xt plus B of delta 2t. So let's take an example जिससे आपको ये basically clear हो जाएगा. We have a van der Waals oscillator. Van der Waals oscillator is actually a classical example of a non-linear system. इसमें दो differential equations है जिससे basically the mathematical model actually involves two differential equations, x1 dot equal to x2, and another differential equation is x2 dot equal to mu 1 minus x1 square x2 minus x1. ठीक है. So there are two equations in this term, and where mu is the coefficient of this oscillation and x1 dot and x2 dot represent the mathematical model of the system. So this is now a non-linear model of the system. This is a non-linear equation of this particular system. To linearize this using small signal analysis, what we can do is we need to first of all find out x dot equal to 0, and we need to substitute x dot equal to 0 and find out the equilibrium points of this system. Okay? So once we substitute x dot equal to 0, you basically get x1 dot, x2 dot. Let's first put this in the matrix form. x1 dot equal to x2, x2 dot equal to this equation. Let's put this in the matrix form that we actually understand. x1 dot and x2 dot. Now we need to substitute x dot equal to 0. That means this matrix x2 mu 1 minus x1 square x2 minus x1 is equal to 0, or in other words you can say is equal to 0 0. So once you do this, what you'll see is x2 is equal to 0 and x2 equal to 0 जब यहाँ पे भी substitute करेंगे, and mu is actually greater than 0 in this case, you will find out that x1 is also equal to 0. ठीक है. x2 equal to 0 यहाँ से डायरेक्टली मिल गया, तो x2 equal to 0 यहाँ पे substitute करके minus x1 is equal to 0, that means x1 is also equal to 0. तो इसके जो ऑपरेटिंग पॉइंट्स है, that means x2 का जो इनिशियल कंडीशन है और x1 स्टेट वेरिएबल का जो इनिशियल कंडीशन है, that is equal to 0. ठीक है. हमारे पास एक सिस्टम है, उसका मैथमेटिकल मॉडल ऑलरेडी दिया हुआ है, x1 डॉट इक्वल टू x2, x2 डॉट इक्वल टू म्यू 1 माइनस x1 स्क्वायर x2 माइनस x1. So as I said, the first step is actually to find out the equilibrium points of the system or the operating points of the system. और वो हम कैसे निकालते हैं? by substituting x डॉट इक्वल टू 0. x डॉट हमारा यहाँ पे x2, ये दो इक्वेशंस है, तो यहाँ से तो हमें डायरेक्टली x2 इक्वल टू 0 मिल गया, और जब हम x2 इक्वल टू 0 यहाँ पे सब्स्टिट्यूट करेंगे, x1 विल बी ऑल्सो इक्वल टू 0. बट विच पॉइंट्स? x2 0 is 0 and x1 0 is 0. The operating points or the equivalent points of the system are actually equal to 0. So what will be the state space model of the system now? For the linear model now, it will be nothing but जैसे मैंने आपको पहले बताया, A matrix will be nothing but delta F1 by delta x1, delta F1 divided by delta x2, delta F1, delta F2 divided by delta x1, delta F2 divided by delta x2 at x0. ठीक है. डेल्टा F1 हमारा क्या है? F1 is the first equation, and first equation is, this is our first equation, F1, and this is F2. F1 is x1 dot equal to x2. So once you f1 dot is equal to x2. That means x2 हमारी इक्वेशन है ऑन द राइट हैंड साइड, डेरिवेटिंग इज रेस्पेक्ट टू x1, x2 का पार्शियल डिफरेंशिएशन विद रेस्पेक्ट टू x1, and this is delta x2 divided by partial derivation of function number 2, and delta f2 divided by delta x1 हमारी जो फंक्शन नंबर 2 है that is mu 1 minus x1 square divided by into x2 minus x1, इसका partial differentiation with respect to x1, so you have mu 1 minus x1 square x2 minus x1 and delta by delta x2 of mu 1 minus x1 square x2 minus x1, ठीक है. You have function 1 and function 2 deriving them, उसका partial differentiation with respect to the state variables x1 and x2. The partial differentiation, once we do the partial differentiation, delta x2 by delta x1 is nothing but 0. Delta x2 by delta x2 is 1. Delta by delta x1 of this equation, इसका differentiation क्या आएगा, mu into 1 minus x1 square, that is mu into 1 minus this is mu x2 minus mu x1 square x2, that is mu x2 का तो 0 हो गया, this is minus 2 mu x1 x2, ठीक है, and minus x1 का हो गया सीधे ही -1, and then differentiation of this equation with respect to x2 के साथ जब हम डिफरेंशिएट करेंगे तो ये सारी टर्म कांस्टेंट हो गई, तो यहाँ पे mu 1 minus x1 स्क्वायर आएगा, ठीक है. आपके पास दो इक्वेशंस है. फर्स्ट स्टेप इज फाइंडिंग आउट द इक्विलिब्रियम पॉइंट्स x2 नॉट एंड x1 नॉट, तो हमने निकाला व्हाइल सबस्टिट्यूटिंग x डॉट इक्वल टू 0. In other words, you have to simply put these two equations equal to 0 and you have to find out the values of x1 and x2. वो हमने किया. उसके बाद first of all find out the differentiation of this with respect to x1, that is 0. Find out the differentiation of this with respect to x2 of this term with respect to x1 is 0, with respect to x2 it's 1. Then differentiation of this with respect to this whole with respect to x1 and then with respect to x2. तो ये आ रहा है आपका, this matrix is coming out, this is your A matrix, but this is at x naught. अभी हमने x naught के वैल्यू सबस्टिट्यूट नहीं किए. x naught क्या है? x naught is basically x1 0 is also 0, x2 0 is also 0, so you have to actually substitute x1 and x2 both equal to 0. तो यहाँ पे क्या आएगा? This will come out to be, this will simply reduce to once you substitute x1 equal to 0, x2 equal to 0, this will be 0, 1, this will be -1, and यहाँ पे x1 is 0, this will be mu only. So A matrix will be 0, 1, -1, 0. Mu, sorry. This is how you do it. आपको पहले ये जो आपका नॉन लीनियर मॉडल है, approximate this equal to 0, find out x1 0, x2 0, x3 0, जितने भी स्टेट वेरिएबल्स हैं. इस केस में दो ही स्टेट वेरिएबल्स थे, x1 0 और x2 0 हमने पहले निकाला, इनिशियल कंडीशंस निकाले x1 0 और x2 0. Once you get that, then differentiate these two equations, partially differentiate these two equations with respect to the state variables. You will find out this matrix A. Once you find out the matrix A, put the initial conditions in, you will find out this is your matrix. अब यहाँ पे इस केस में particularly इस केस में क्योंकि there was no dependency on u, x1 यहाँ पे ना तो इस केस में कहीं पे u है ना तो इस केस में कहीं पे u है, तो there is no B matrix actually in this case. So we cannot find out the B matrix in this case. खाली यहाँ पे A matrix है. So in other words, you can now say that your linearized model is something like this. x dot equal to ax, or x1 dot x2 dot will be equal to 0 1 minus 1 mu times x1 x2, ठीक है। बी मैट्रिक्स यहाँ पे इस केस में नहीं है तो वो प्लस 0 टाइम्स यू है। So this is your system and this is your linearized model of which system। जो हमारे पास सिस्टम क्या था, हमारा सिस्टम हमारा ये था, this was our original system, the non-linear model was this, fine। So to find out its linear approximation, differentiate each term with respect to the state variables at its equilibrium point or at its initial condition, ठीक है। So this you have obtained finally, so this will be the linear model of that non-linear equation। So we can use this model instead of the non-linear model now to analyze the behavior of the system। Now if we have this equation, we can say this system will be having, इसके जो आइगन वैल्यूज होंगे वो क्या होंगे, substituting lambda I minus a equal to 0, you can find out the values of lambda 1 and lambda 2, that means lambda I minus a, lambda I minus a equal to 0, so this means lambda square minus mu lambda, lambda square minus mu lambda, plus 1 I guess, plus 1 equal to 0, so lambda 1 lambda 2 जो इसके रूट्स होंगे that will be minus b, that's plus mu, plus minus under root of b square minus 4ac, mu square minus 4ac divided by 2a। so these are the eigenvalues now of this system। so you can now say for if mu is greater than 0, for what values of this system will the system be stable, and for what values of this for what values of mu can the system be unstable। now you can basically directly say it from this system, ठीक है, from the linear model। now in a van der Waals oscillator basically यहाँ पे mu अगर हमेशा 0 से ज़्यादा होगा, lambda 1 lambda 2 will always be positive, that means this system is actually unstable। so this is actually the van der Waals oscillator। ये हम एक्चुअली इसकी जो इक्वेशन है वो हम बाद में डिराइव भी करेंगे, यहाँ पे मैंने खाली एक एग्जांपल दिया आपको, how you basically linearize a non-linear model using the small signal analysis, fine। so what you have to do is first of all substitute x dot equal to 0, find out x naught and u naught, इस केस में u naught नहीं था। once you do that then differentiate, partial differentiation with respect to the state variables, delta all the differential equations। ये जो मैट्रिक्स बेसिकली है, this is known as Jacobian matrix। this was your system। so first step is substitute x1 dot substitute x1 dot equal to 0, substitute x2 dot equal to 0, find out the initial conditions of this matrix, ठीक है। x naught और u naught आपको निकालना है, इस केस में u naught नहीं है। after you do that you have to basically find out the matrices A and you have to find out the matrices B, where A matrix is actually delta f1 by delta x1, delta f1 divided by delta x2 up to delta xn, and delta f2 divided by delta x1, delta f2 divided by delta x2। so these जितने भी functions होंगे, जितने भी state variables होंगे, partial differentiation with respect to each other, and you will find out this A matrix। this A matrix is known as the Jacobian matrix, and you might or you may be studying this in past term 3 also, ठीक है। you'll be finding out the delta Jacobian matrix in that case also, ठीक है। वहाँ पे हम basically जितनी भी पावर इक्वेशन होगी, वोल्टेज इक्वेशन होगी, we differentiate them with respect to each other and find out the Jacobian matrix for analysis of the system. यहाँ पे अभी वही है, आपके पास n differential equations हैं, partially differentiate them with respect to the n state variables, that gives you the A matrix. Partially differentiate all the differential equation with respect to input matrix, that gives you the B matrix. ठीक है, and once you do this, substitute these initial conditions in here, you will find out A, you will find out B, that will give you the linear model. और जब हमने इस वैंडरपोल्स ऑसिलेटर का लीनियर मॉडल निकाला, इट बॉयल्स डाउन टू दिस. नाउ दिस इज एक्चुअली अ सिंपल सिस्टम जिसके साथ हम कोई भी एनालिसिस कर सकते हैं. वी हैव फाउंड आउट द आइगन वैल्यूज ऑफ दिस सिस्टम बाय सबस्टिट्यूटिंग lambda I, determinant of lambda I minus equal to 0. We have found out that lambda 1 lambda 2 will be this. Since mu is actually always greater than 0 for a van der Waals oscillator, so this will always be positive, these eigenvalues. So this system is actually a representation of an unstable system. Directly from the nonlinear model, you would not have said whether this system is unstable or not. This is the first method of linearization through small signal analysis. इसके बाद आपका piecewise linear approximation है और harmonic analysis है. That we'll do in the next session, inshallah. I hope this is clear, this method. Any questions? आपका दूसरा क्वेश्चन है, लेट मी नो एक्स डॉट, लेट मी नो व्हाट इज ए मैट्रिक्स. अगेन इस केस में बी मैट्रिक्स नहीं होगा. ए मैट्रिक्स ज़रा मुझे जल्दी से बोलो क्या आएगा लीनियर सिस्टम का.